Okay, thank you. So yes, I was asked to to give an overview of stellar convection, but basically we've only been talking about that, or mostly talking about that, since I've been here and at this conference. And there are many people here who know so much more about that. Usually people ask me to talk about diffusion, not convection, different type of transport. So, I was here last week and I talked to a lot of the participants, and basically I've heard a lot of people telling me we want to know about convective boundaries in 1D stellar evolution codes, which is basically what I know best. So that's mostly what I'm going to be talking about. So this is more going to be that. So something else is that, well, everybody's been doing some experiments this week, so I decided why not me. So I'm using a totally new font. It's unpatented, and it's called Ant's handwriting. And if you have a problem with the font and you cannot read my slides, raise your hand and I'll read whatever you cannot read. And then the next thing is that I don't want this to be really a review talk. I'd rather have it be like a lecture. So I'll try to go slowly. I've been told many times I speak way too fast. So I'll try to be slow. If I'm not, you do that, and I'll try to slow down. And the other thing is I would like really the audience to raise their hand and ask questions and interrupt me whenever. I left lots of time for that in my talk. Because I realized also yesterday that lots of people don't know the jargon, have no idea what a 1D stellar evolution does or is. So raise your hand and I'll try to answer whatever question you have, and I'll try to help you with understanding what I'm talking about. So please try to make it interactive and raise your hands. And I've told the mic will circulate in that case. So there are three mechanisms that work for heat transfer: thermal diffusion, which is what I know. It's well understood, well modeled, which is probably the reason why nobody talks about them anymore. Radiation is pretty well understood, reasonably well modeled, except that it depends on opacity, and that is not so well known. And then there's convection, which is not well understood and poorly modeled. Convection is a hydrodynamical instability that arises in a stratified fluid with a sufficiently large temperature gradient, and I'll be talking a lot about this temperature gradient. So it's a large-scale motion which takes hot matter upwards, cold matter downwards. So there's transport of heat, and there's also mixing of chemical elements. So how large does the temperature gradient have to be? It's easy to show by little animation of blob, little hand waving with blobs. You take a blob of matter in a stratified medium with a temperature gradient. You take it up, it will expand adiabatically. And then when it is in pressure equilibrium with the surroundings, you look at its density, and if the density of the blob is larger than the surrounding velocity density, it will sink back. That's stable. If it's smaller, it will continue to rise, and it's unstable. It's easy to show that that leads to a criterion for instability, which can be written in terms of temperature gradients. So radiative temperature gradient larger than adiabatic temperature gradient means instability. This is called the Schwarzschild Criterion, and I assume you've all heard about that, maybe not. And so for that to happen, because the radiative gradient depends on opacity and on luminosity and temperature, you have several possibilities. Either you have a large opacity, and that happens if you have, for example, partial ionization regions, or you can have large luminosity, which happens if you have nuclear burning. I want to point here that there is another criterion that people use sometimes, which is the Ledoux criterion, which is that the grad has to be larger than grad ad plus grad mu, where grad mu is a term that depends on the composition gradient, which is positive in stars. So this is a stabilizing effect, but I'll talk much more about that later. So in stars, in high mass stars, hydrogen is ionized in the envelope. The opacity is low, so you have radiative envelopes. The radiation gradient is small. In low mass stars, hydrogen is not ionized in the envelope. Radiation can be easily absorbed. You have a high opacity, and you have convective envelopes. This is a schematic. You also have other cases, but it's smaller. In the cores, you have energy production through nuclear burning. If the burning happens through the PP chain, which is what happens in low mass stars, the energy is not very dependent on temperature, and so the radiation can handle the heat flux. You have radiative cores. In higher mass stars, the cycle is combustion is CNO cycle. The energy is very dependent on temperature. It's very steep. Radiation cannot handle the flux, and you have convective cores. So basically, and then you have also shells with nuclear burning, and you have those shells can be convective, not always. So whatever the mass of the star, it has convective regions. So the questions we want to answer is, where are they exactly? Basically, where do you put the boundaries between the convective regions and the radiative regions? And that's what I'm mostly going to talk about. How to model these convective regions. It's turbulent. It's intrinsically 3D. It's complicated. Well, we get rid of all of that in 1D evolution code by going to mixing length theory. And then you want to know the resulting mixing and energy flux. Well, you might as well take that from your mixing length model. And then you have interactions with magnetic fields, pulsations, nuclear burning, etc. That's much more complicated. I'm not going to talk about that. Especially since after my PhD in plasma physics, I told myself I would never deal with magnetic fields again. I'm trying really hard to do that. So in most 1D stellar evolution codes and in the MESA instrument software, we need a 1D model for the convection to put into this 1D code. So the mixing length model was basically invented at almost a century ago. And I tried to read the original paper, but it's in German because at the time not everybody actually wrote in English. The papers were published in people's home language. The theory that's mostly used in stellar evolution codes is the Bohm-Wittense from 58, so it's also very old, and it's still the most widely used. What is the reason for that? Well, it works, basically. It generally gives very acceptable results. There's a free parameter that people can adjust. And so because it works, we use it. Also because 2D and 3D simulations of convection are absolutely not ready to be included in 1D stellar evolution codes. Therefore, we do use what we have, and that actually works not pretty well. So what's the mixing length approach? It consists in saying that we consider that mass elements travel some distance, LC, which is called the mixing length, adiabatically at some velocity, VC, and they release the heat when they reach pressure equilibrium. So it's actually, you can show that, I'm going to try to use this. So the change of temperature due to this motion is proportional to the difference between those radiative and adiabatic gradients. It's proportional to a length scale, which is the pressure scale height, and then there is this length, which is the mixing length. So we usually define what is called the mixing length alpha parameter, which is the ratio of the mixing length and the pressure scale height. And alpha is order 1, 2, something like that. So but it is a free parameter, and the flux of heat is also determined in terms of the difference in those gradients and the mixing length. So that mixing length has some importance, and it's a free parameter which cannot be determined from first principles. Hopefully 3D simulations will help us put some reasonable number there based on physics. So convective boundaries, where should we put convective boundaries? Well, convective boundaries are where the convective velocity vanishes. Velocity, not force. Not buoyancy force. It's where the velocity vanishes. Within MLT, that's equivalent to say that it's where the radiative gradient, temperature gradient, is equal to the adiabatic temperature gradient. So this is where things get interesting, because velocity, a convective velocity, can only be defined where there's convection. So saying that the velocity must vanish, which means that grad rad must be equal to grad ad, means that has to be true in the convection zone, within the convective region. So we need to have grad rad equals grad ad at the convective boundary on the convective side. And that's what leads to a lot of problems, and I'm going to show you many of that afterwards. But as an important consequence of this, using the Ledoux criterion or using the Schwarzschild criterion should not make a difference for the position of the convective boundary. If it does, something's wrong with your way of determining your boundaries. And I'm going to show that later. At least, you know, if you assume that the convective region is one mixed, because then you don't have a grad mu. Ledoux, Schwarzschild, same thing. And because you don't use whatever happens in the radiative region when you do that. And that's not usually done correctly in stellar evolution codes. Many times it's not done correctly. Why? Well, because usually people use the find the zero of grad rad minus grad ad. But if you have composition discontinuities, that is ill-defined. By doing that, you use data from the radiative region, find the zero, right? So you use data from the convective side and from the radiative side, and you go through a discontinuity in composition, and that leads to big problems in the positioning of the convective boundaries. It also is a big problem during core-helium burning. And core-helium burning is a really tricky thing for the boundary of the convective core, because the radiative gradient acts very weirdly there, and I'm going to show you that later. No question? Yes.
Can I just ask a clarifying question? Adrian Fraser, can I just ask a clarifying question? So you said that the position shouldn't depend on Schwarzschild versus Ledoux, right, but the condition for instability changes between the two, right?
No.
Okay.
I mean, yeah, but you will see that here I'm not talking about, I'm talking about, you see that they will give the same thing, so your convective region will be the same.
Thank you.
If you do it correctly. So I'm going to give a few examples that I'm going to go through slowly, and I hope you, because you know, which are basically, because I'm come from astereosismology of B stars, I'm very interested in convective cores. I'm also interested in astereosismology of white dwarfs. I'm also interested in cores, and so all my examples will be about cores, convective cores, but we can do that also for surface convection zones and things like that. So the three examples I'm going to talk about in detail are the case of a low mass star, which has a growing convective core on the main sequence. I'm going to talk about a high mass stars that has a retreating convective core on the main sequence. And I'm going to talk about growing convective cores during core-helium burning. Okay. So this is where, if you have questions, raise your hands, because I'm going to show you pictures, figures that you are maybe not used to. So I'm going to show you a lot of figures where I'm going to plot as if these are profiles inside the star. So this is the mass, the mass coordinate. This is, I'm going to put there some temperature gradients and also hydrogen profile. So this is what you have for these profiles if you do find the zero method. So what happens is you have the adiabatic profile here is almost flat, doesn't change much. The radiative gradient is the red line here. You see that it does that, weird thing. And then you have the adjournment profile, which has a discontinuity at the boundary. And so, as you can see, the dashed, the purple part here is the convective region, as determined by the find the zero method. At the boundary, the radiative gradient is not at all equal to the adiabatic gradient. In fact, it's bigger. So this means that in this whole region, you have grad ad larger than grad ad, and it should be convectively unstable. And in the model, it's not. So this means that we have not done the job correctly of putting the boundary condition at the right place. And this is what is done in many evolution codes, many. Right. So what that does is actually, if you do that, it prevents the core from growing correctly. So this is the mass of the convective core as a function of age. And if you don't do things correctly, the core basically doesn't grow the way it should. Yes.
This is Adam. So I'm just wondering, it looks like that region is Ledoux stable. Is that right?
Yeah, so yes, the blue is Ledoux.
Okay, so that's why the code is identifying that as a stable layer, not a convective layer, right?
Yeah, but you are not, the criterion has to be applied on the convective side of the boundary, and on the convective side of the boundary.
Okay, got it.
It's smaller, right? So that's why the find the zero method does not work, because it takes points from the radiative region to decide where the boundary is, and you can only do that by taking points from the convective region. So.
All right, Anne, this is Daniel. Can you explain why you need to take this on the convective side and not the radiative side?
Because because the boundary has to be where the convective velocity vanishes. The convective velocity is only defined in the convective region. There is no convective velocity outside of there. Okay. So you have to make sure that the velocity vanishes at the boundary. That can be done that can be related because the velocity is proportional to the difference between the gradients. You can turn that into grad rad equals grad ad, but where the convective velocity is not zero. You have to come from the convective side.
Okay, so from my perspective of someone who does simulations, is a statement that with a setup like this, the velocities would not be zero at the boundary.
Exactly. And
because of that, the motions would actually extend past, and that means that it's going to be a bad.
This is exactly what happens. This is exactly what happens. Whatever little thing you have here, it's totally unstable to convection.
Yeah, this is Evan. My perspective on this has sort of been that, as Daniel's referring to, if you have any motions at all, which you kind of would expect in this top left panel, any small amount of mixing will basically wipe out that Ledoux stabilizing term, and therefore you should be able to propagate this boundary outward.
Even diffusion does it, but very slowly. But not fast enough. But anything, this is unstable. This is not a stable boundary. And so it should, physically in real life, it will move to the right. And so the code doesn't capture that. So we have to do something. Right. Any other question? Because this is the core of what we're going to be talking about.
And you definitely just answered this question, but I just want to make sure. So you're saying that Adrian Fraser, thank you. The reason you say that it's unstable, despite what one might think, it's because grad rad is greater than grad ad at that part, on that side. Okay, thank you.
So, at the boundary. I'm talking about the boundary here. I'm not talking about here. I'm talking about here. So here, grad rad is larger than grad ad. And in the convective region, this means the velocity is not zero. This means this is not the boundary. Okay, Yes.
Hey, Ann, this is Evan Anders. So I agree with everything. I'm just wondering on the right panel,
So I'm coming to that.
oh, we haven't got there yet. Okay, I was just gonna say, like, why is that like a different situation from the one on the right? Because it looks like the grad rad is still greater than grad ad on the right side of the boundary. Here, oh, it's on the convective side again. Okay, yep, we're good. Okay, that makes sense. Thank you.
The velocity is 0, right? So we've been spending a lot of time, which Thompson and me, for several years, working on trying to solve this problem. And it was not so straightforward to achieve that. But we managed to make a lot of progress. I'm going to show that today. So in this right panel, in this situation, so you imagine that here, I'm going to tell you how it works in Mesa. Really, the algorithm part, because that's going to help you understand how it works and help people who have questions, because I've heard a lot about that. So grad rad is larger than grad ad. So that means that if we were to increase a little bit this, add like the next zone into the convective core, let's see if that's enough to bring grad rad equal to grad ad in the convective region. We're going to mix in more elements. So that's how the first, we have two algorithms. So the first one does that. The first one adds the shell that's outside the current wrongly positioned core, sees if it's stable or unstable. If after adding this shell, that boundary is stable and stable, do we still have grad rad larger than grad ad or not? If it's still larger, we continue like that. If it's smaller, we say, okay, we found the boundary, right? This is what we do here. And as you can see, the core gets much bigger. We have the correct boundary condition here. The velocity vanishes, the convective velocity vanishes. So we are happy. And the core does what it's supposed to do. The convective core, it grows, and then we see that's what happens for low mass stars on the main sequence. Everyone happy with that? So, I don't know if I talk. Yes. So that's what we had before. You know, the part where I'm happy. Except we were not so happy because there was still this bump here. And so we found out how to do it better. That's the convective premixing scheme. By actually, when we add shells to the core, because it's not yet at the right place, we actually recalculate all the chemical composition. We remix the region. We don't keep what we had before within the trying to fit the boundary correctly. Before we just increased, keeping the composition we had before. Here we remix every time at each subtime steps, and that actually leads to flattening here of the radiative gradient. So we have a adiabatically neutral region, which is usually called semi-convective region. Doesn't change the size of the core that was fixed before because we had it at the right place, but it makes sure that the gradient makes sense just outside of the core, and that has consequences on the composition profile just outside of the core. Now this is where, not yet. Does it come later? Yeah, it comes later. So this is for what we have for crying core. What about the retreating core in the main sequence? People have always been very happy with what happens there. This is the no, this is predictive. This is an example where I've used Schwarzschild instead of Ledoux, so always the same profiles, temperature gradients, composition. This is what we have if we do the find the zero thing. It actually puts the convective boundary of the core at the right place. No problem there. but it's a mess of convective shells above the core. And these leave behind step-like composition profiles, which are messy and which make the Buhn-Weisslar frequency, which is so important for asteroseismologists, really weird, not behaving. And that is going to have an influence on how you do asteroseismology of P stars, for example. So the reason you have that is you have this mess of little convective shells. And if you look at the convective shells, inside the convective shell, you have regions where at the boundary, the radiative gradient is larger than the adiabatic gradient. So you know that's not a situation that's physically acceptable. The boundary of the convective region is not there. So we apply our new scheme, and that leads to this kind of situation where, you know, the boundary of the convective core is still at the same place, no problem there, because the problem is with the convective shells above the core. And now we don't have this mess of convective shells above the core. We have a nice, very smooth, very well-defined semiconvective regions. That's without applying any type of semiconvective formula or whatever. This just comes from making sure the convective boundary is placed correctly, physically. And you don't have, yes.
This is Adam Germain. So just so I understand the process, so you started with a convection zone that extended all the way to mass coordinate 7, say, and then as it's retreating.
No.
Oh, okay.
No. We start from a situation, okay, in this case, we started from this.
Okay.
So this is obtained with our first algorithm, which solves the problem, which was supposed to solve the problem, but here it doesn't do it. You still have the predictive mixing. You still have this place here where inside the convective region, the radiative gradient is larger than adiabatic gradient, and so you have a non-zero velocity. Mm-hmm. And so we just let that, so we start from that, and I think I have the movie. Yeah, this is the movie, it's in the paper. It's a movie, I mean, it's 6 snapshots of a movie, and it's in the Mesa paper. You start from something like that. You apply the premixing scheme, and that shell will actually evolve in this way. So it will move inwards here. It will slightly move outwards as well. You will see later. And you do that, and you let it go. And then at the end, you have this.
Okay, thank you.
So it does it by itself, even if you start from something that's not right.
This is Daniel Quene. I'm a little bit confused about how to interpret these semi-convective regions, again, in the context of being a 3D modeler, where there's overshooting motions which go beyond the convection zone. So in a 3D simulation, the velocities are not identically equal to 0 at the boundary. And
then that's not the boundary. The boundary, by definition, is where the velocity is 0. And in my opinion, this is something that we have to discuss here. But in my opinion, the boundary is where the velocity is 0, because then your convective elements will not go further. So that's where it will stop.
All right, but I guess, so even, so of course there's differences between what happens when you do a simulation and how you want to model things in 1D. And the process that I'm thinking about in the context of 1D is that I'm imagining that you have some convective motion which goes beyond like the mass coordinate of 4. And if it does go beyond that, I think it would be neutrally buoyant as it continues going upwards.
You mean here?
Yeah, because I see that grad ad is equal to grad rad.
Yeah.
And because of that, it seems to me like it would be able to mix that region up relatively effectively. And because of that, the chemical composition should be relatively uniform. But if I understand correctly, if you did actually make the composition uniform between 4 and 7 in your semi-convective zone, then you would actually say that grad rad is less than grad ad, right? It would be stable. So is that why we think that this might be a kind of stable configuration? I mean, it's about the opacity dependence on
yes,
on
exactly.
X, right?
That's the whole thing.
Yeah. Okay.
I'm going to say a few words about that. Opacity is what is doing this thing. The opacity is the most important ingredient here, and the fact that it changes when you mix.
This is Evan Bauer. So maybe I'm not totally following your question, but in that bottom right panel, it wouldn't be completely neutrally buoyant because the Ledoux gradient is much greater than the adiabatic gradient. And I think the thinking is in this region, the mixing is not efficient enough to completely wipe that out. Does that get toward? Okay.
Right. Thank you.
This is Adam Germain. So a somewhat different question. So was the convective core at some point at a mass coordinate greater than 7?
No, this is a retreating core.
It's retreating, right?
It's retreating.
So was it at some point in the past?
Yeah, of course, yeah.
Okay.
It's retreating.
So if I hadn't started in the top left,
yeah.
If I'd been using CPM from the beginning,
yeah. You'd get that.
I'd get that, and that would be because I would be identifying the correct location for the gradient at every time step, and so as it retreats, it will just trail that.
Right.
Okay, that's very helpful.
Yeah.
So this was with convective premixing for the whole time?
Yes.
Okay.
If you have predictive, it's here. You still have the shell, and if you do it better, you don't have a shell anymore. You have a semi-convective region above the core. It doesn't change much. Basically, it almost doesn't change the convective core size. So this is mass of the convective core versus age. It does leave behind, on top of the core, partially mixed region with a smooth composition profile. That should have an influence in asteroseismology. Okay. So this is also why Adrian is going to kill me. So he asked last week why I went to the Sommerhalin meeting. Basically, it was to have a list of people I could put on paper and which will be sent to the police if I die a suspicious death. In 1970, Maurice Gabriel, who was at the same university I'm in, so I know him, wrote a paper where he says, we give arguments to show that the experiments performed by hydrodynamicists on Sommerhalin convection might not be very relevant for our problem. Sorry. He says it, not me. In particular, it may be concluded that the opacity dependence upon hydrogen abundance is an essential condition to the appearance of semiconductive zone in stars. And that's exactly what we see in MESA now with CPM. That's exactly what we have. So I'm not saying Sommerhalin doesn't happen somewhere in the star, but maybe that's not what's necessary in all the time. And I don't know enough. That's why I came to the meeting about Sommerhalin mixing to know where it would be acting in stars. But this is a very interesting paper because he did all of that we now see in MESA from, calculations, no computer. And he has this exact same conclusion. So you had a question? Or someone?
Yeah, Adrian Fraser. So is this argument is saying that those zones should not be unstable, or that we shouldn't get semi-convection?
Right, but I'm not as familiar as you. But how would you have Sommerhalin mixing here? You can tell me. I want to learn. That's why I went to the meeting. But
okay, just make sure I'm understanding. Okay, thank you.
All right. So now coherent burning. I still have some time, and that's so much harder because what happens is that the behavior of the radiative gradient during core helium burning is really weird. So you start at the beginning with some, regularly behaved radiative gradient, and as the star evolves, the radiative gradient starts to have like an up part. It shows a minimum, and that minimum, as you increase the mixing of helium, this minimum will go down, and at some point it will reach the adiabatic gradient. But if you let it go, it will just go further and go below it. And at that point, you will have splitting of the convective core, because if these go down, like this, you will have the convective core stops here and then another shell up here. But the shell above that core would not obey the Schwarzschild or the Ledoux criterion, because it would have, a shape like, I don't have it here. I need a blackboard, but anyway, so we can I'll show you later, but it will do something like this. So it will go down, it will go back up, and then it will come down there. So at this boundary, you would have something that's unstable to convection. So we have to treat that. So the first people who tried to do that were, I don't know if I have their paper here now, Constantino et al. In the Monash code. They did a lot of work to try to make the convective core on the core helium burning phase large and not have this splitting of the core. They did that by introducing some kind of overshoot, which depends on several parameters, at least 2, maybe more. And they called their scheme maximal overshoot. This was the maximum size of the convective core they could do. So inspired by that, convective mixing, predictive mixing was inspired by their work, except we didn't want something that was an ad hoc diffusion, overshoot, whatever. So we did it using our scheme, predictive mixing scheme. And the only thing that we do in the scheme that's actually a bit special is that we never let this go below the adiabatic gradient. We never let the radiative gradient go below the adiabatic gradient. And in the predictive mixing, this means we still have some part here at the boundary which is not correctly done because it's still convectively unstable. So CPM gets rid of the problem. If you apply that scheme, it actually develops here a convectively stable region, semi-convective region, and the profile of grad rad at the end, as the star evolves, is like that. It goes down. It's here adiabatically stable. It's grad rad equals grad ad, and it continues like that. If you look at what is in this, I found that in a paper and I forgot to put it's one of the, it's not Constantino, it's, anyway, I'll find it. They argued, hand waving, that this is what you should have. This is what should happen, but they didn't do it in numerically, but they said this is what should happen from physical arguments. And now we have exactly that by doing the mixing correctly at the boundary, simply. So that means that instead of having with the 0 point, find the zero method, the core during core helium burning gets stuck as soon as you have splitting of the core, of the convective core due to the radiative gradient going below grad ad. The core doesn't grow. As a consequence, the age on the core helium burning phase is really small, very, very small. Not at all in correlation with observations. So we know that something was wrong there. So now with the new scheme, the core is allowed to grow as much as it can, and you have ages that are okay with what we observe. In the CPM scheme, we have actually the convective core gets stuck also at this point, but above it, we have a semi-convective region that develops. So we have exactly the same, in both schemes, exactly the same size for the mixed region, but different composition profiles above the core. CPM is much better because it's physically much more motivated. The problem with CPM is that we cannot get rid of what is called the Bayes impulses. I'm going to talk a little bit about that if I can continue. Yeah? Okay. One thing. So the predictive mixing scheme, the one at the top, gives results totally compatible with the maximal overshoot in the Monash code, except that in their case, it's not physically motivated. Okay. Should I go to the end or we stop for questions? We already stopped you a lot. So okay, I continue. So these people study SDB stars, and they recently published a very, very nice paper at the beginning of this year, where they used MESA and the new convective boundaries schemes, and they explain, for those of you who don't understand what I'm talking about, they want to understand better, read that paper. They really explain clearly, very clearly what we do in MESA, in more words than we were allowed in MESA 4 and MESA 5. and they're really right in everything they wrote about it, so they really understand the schemes perfectly, and they really detail it in the paper. It's very well written. So SDB stars are just helium stars that are on the core helium burning. They are special because they lost their envelope and things like that, but it doesn't matter. The core is the same as any core helium burning star. And so here they have, in their paper, they show Kippenhahn diagrams of that stage on the core helium burning. So the top is what happens if you use the find the zero method that many codes use. This is predictive mixing. This is convective premixing, the best one, where you actually develop a convective core and a partially mixed region. The problem is that at the end of the evolution on the CHEB, I'm going to talk about that later. At the end of the combustion of hydrogen, of helium, when you ingest a new shell, it's going to have some fresh fuel that is going to put in the core. And the problem is that you're going to inject a very tiny amount of helium in a core which is depleted in helium. It's going to rush to burn at a very high rate because at that point, it's not triple alpha, it's carbon plus helium gives oxygen, which is going to give you a lot of energy. The luminosity is going to increase very suddenly. Your convective core is going to increase very suddenly. Your mass, so you're going to have spikes of luminosity and mass of convectivity. That's not right. I mean, why would the tiny? I mean, physically, you have this huge star. We tried slowing down the ingestion of helium, it didn't work. I mean, we tried all kinds of things to try to slow down that process and get rid of those freezing processes. We couldn't. So that's where the 3D people might be useful. So just one thing I wanted to add is that some people, some aseosismology people claim that the cores we have on the core helium burning are not large enough. We should do like we do for main sequence stars, add some ad hoc overshoot and have the core bigger. The problem is in doing core helium burning, if you add overshoot, it does a lot of messy things. It doesn't make the core bigger, never. There's no way we can do it, make it bigger. So in this case, the purple is the overshoot. So the only thing that it does, it kind of make all these variations in the core size, it messes things up completely, but it doesn't increase the size of the core. Even that this is if you use standard mixing, find the zero method, because why not? And so it doesn't increase the size of the core, it just makes the whole internal profile very messy. So that doesn't work. So Up to now, I don't think anybody can make the core during coherent burning bigger than what we have now with the new schemes in MESA and what Constantino did. Yeah, this is the profile of the core, convective core. The black dots, the black lines are the with convection. Okay, do I have anything else important? No, it was just, I just wanted to say why it's important to have the convective core burning done correctly. Basically, it's because the profiles for carbon, oxygen, etc., at the end of the coherent burning phase are exactly the ones you're going to have at the white dwarf. They don't change afterwards in the evolution. And now we do a lot of astereosismology of white dwarfs, which gives us information about internal profiles and the CO ratio at the core, things like that, size of the core. And so as long as we don't do that correctly during the coherent burning phase, it's hard to do precise astereosismology of white dwarfs using MESA, for example. So I'm going to let you, I mean, I could say other things, but time is up.
All right, and would anybody like to start us off with a question?
Hey, this is Meredith, and hi, Anne. We're going to talk about this again, but now in public. Are there any situations in which predictive is the better choice over CPM?
Okay, yes. One thing that I did not have the chance to mention is that with predictive, we use the diffusion, we mix the convective region like with the diffusion coefficients. With CPM, we mix instantly. So in cases where the mixing is not really faster than some other things that happen, CPM will not give you the correct answer, I would say, because you are mixing too fast. So the scheme has that problem. And then with CPM, we cannot prevent the breathing pulses. With predictive mixing, we have a way to prevent the breathing pulses. So that's the two cases where I think CPM should not be used. If you really do not want the breathing pulses, and if you have situations where the mixing cannot be considered as instantaneous.
Hey, Anne, this is Evan Anders. Thanks for the nice talk. I have a really naive question about mixing length theory. So you mentioned that basically like mixing length theory says like your blob of fluid rises till you're in pressure equilibrium and then you dissipate heat. But at low Mach number, I would assume that the blob is almost in pressure equilibrium and that length scale would be small. But I know mixing length is like something like the pressure scale height. So where's my intuition just like not matching up there?
I don't talk in Mach numbers. Okay, that's the answer. So you can discuss and explain to me better what you mean. Okay.
Hi, this is Joel from Yale. Could you say a few words also about the converse case of envelope, overshoot, and associated like semi-convective processes there? I understand this may be important for correctly locating the RGB luminosity bump during first acid red giant evolution.
So I'm not sure I understood the question.
Could you say a few words about how this could also be used for the opposite case of rather than retreating or advancing convective core, you have now an advancing convective envelope and envelope overshoot and associated locations of the convective boundary in that case.
Okay, so I don't have any figures to show, and I have not really studied the problem because I'm mostly working with cores, but you can apply the same thing and see what happens. I want to say that, for example, for massive stars with the retreating core, lots of people add this totally ad hoc overshoot that you have in stellar evolution codes. If you do that, you wipe out all I said, because this will, if I can quickly find it. Where is this? Retreating core, coining core, no. Retreating convective core. So if you add overshoot, so you add arbitrarily a big zone that where you mix, you add, it wipes out this region completely. It's got, I mean, this corresponds to, I mean, you would have to have f smaller than 0.001 or something like that, very small. And then if you make it bigger, you wipe that out. So I personally hate overshoot, and I know the people who do massive stars, they say they need it and all of that, but I think that they should start from a situation where it's done correctly and then think about maybe with the 3D results, if it's, what would make the core bigger? Does it need to be bigger? Is it something different? Things like that. But I don't know about the envelopes. I'm not, so yeah. If you need a lot of overshoot to compare with observations, maybe this will not be useful. But I would still do it because you start at least from something that's correct. Yeah.
Hi, Anne, Falk Herwig. I wanted to offer a few comments also on historically where this problem has been discussed in the past. And maybe you can pull up the slide with the hydrogen that you talked about first, with the hydrogen burning core. I think for the low mass star where you had sort of this discontinuity. So I just want to say, if you would have gone to a conference like this in 1995, one of the conundrums at the time that people would have discussed was the carbon star mystery. And the carbon star mystery consists of two parts. At the time, people had observed the luminosity function of carbon stars in AGB stars, and they found that the carbon-rich stars are all very low luminosity, whereas the stellar models at the time predicted carbon stars that had very high luminosity, corresponding maybe to 4 or 5 solar mass stars initially. These were models by Ibn and others. And the problem consists of two parts. The one was that the models for high mass initial masses did predict carbon stars, but there were no observed. But the bigger problem was that how to make carbon stars at very low luminosities. And to do that, you need to have 2 solar mass stars initially that do successfully the third dredge up. And why would models at the time not do the third dredge up? Because you have exactly a discontinuity like that. You have the convective envelope trying to penetrate in mass coordinate into the hydrogen-free core, where you have a lot of helium, so the opacity drops at that discontinuity. And so that was recognized at that time as an issue. And it was also recognized that, well, this discontinuity just prevents you from having third dredge up and forming carbon stars and doing a lot of things, like, for example, doing S process, because in order to do the S process in an AGB star, you need to get this envelope, which is hydrogen rich, in through this tiny little helium layer and into the intershell. And the discussion at the time was that, well, you simply can't have in any numerical realization of nature a discontinuity at a cell phase. And for anybody in the room, I think, who is doing 3D numerical simulations, you realize that you can't have a discontinuity at a cell phase. There's in nature only one discontinuity that really is that small, and that's a shock, and we don't have shocks here. And so there were several solutions to this problem at the time. John Lattanzio had one where he was doing something like you described, pre-mixing. That solved the problem. I think the Belgians had a solution, Moblavi, which was similar to ours.
Moblavi is what inspired us too. Yeah.
So, and the Italians had another solution. Oscar Straniero at the time argued about mechanical stability of the boundary. Our solution was that I implemented in my PhD thesis based on Bernd Freitag's 3D simulation, is to say you can't have a discontinuity, and that's why we introduced this exponential F overshooting, and you don't have to make it physically large, if you don't believe that that is the physical mechanism, that's fine. But what it does do is if you can make it as small as you want, you can make it very, very small as long as you afford to resolve it in grid zones, and it will locally at the boundary eradicate the mu gradient or the helium gradient. And then you just go iteratively and find where the boundary is. And so technically, if you do it with high resolution, the F overshooting finds that as well.
So
And let me make one last comment for the helium core burning.
we have a couple of questions that people are waiting for. If you could get to a question.
Maybe I can answer first one thing.
Okay.
So if you, I started, I was supposed to write something about that in MESA 3 paper, because that's what I wanted to do. So I wanted to use F overshooting and then make the border, put many cells at the border of the convective boundary. That does not converge. That does not converge in MESA. And that's why we went another direction. But increasing the number of cells does not solve the problem. We wanted to do it also on physical arguments, but yeah, that didn't work.
And let me
John,
just comment on the
I
helium
think,
core.
Falk, I think we have a couple of people asking questions. Maybe you could take it offline.
Yeah, thanks. So I have a comment, which is thank you for dealing with such a complicated topic and explaining it very well, but also spending the time on putting this in the code, because I agree it's very important. So my question is retaining to like intermediate mass stars that have these sort of growing, then shrinking, then maybe growing cores, or they sometimes shrink, then grow, and you can do lots of different things in the sort of 1.5 to 2 solar mass range. I'm just curious with these schematics, have you looked at that as well? And I guess the growing, receding, growing sort of washes this stratification out a little bit, and it doesn't matter as much.
I did not do this simulation. So if you have an initial, input to give me what type of star, I can run it and I'll tell you, but I haven't done it, so I don't know.
Yeah, I think that'd be really interesting, and Timothy, I know, would be very interested in that as well for the Gamma Dor stars. But yeah, I agree this is very important, and thank you for explaining it so well.
And I think we have time for one last question, Jamie. That's quick.
Are there particular, Jamie Tyre, are there particular observations or simulations in 3D that you think would allow you to either verify that this is exactly the right way to do it, or falsify that this is not?
Thank you for that question. And this is where I come to my last slide, which I forgot to put up earlier. From what I understand, it's very rare that in the 3D simulations you take into account the opacity, including how it will change when you mix at the convective boundary. And that's essential here. This is very essential. So you really have to do that. You really have to, that's my takeaway for the 3D people. You have to put in your simulations the opacity and how it changes when you mix at the boundary. And also, if you are in a burning region, the elements are gonna, the chemical element composition is going to change. Take that into account as well. Those are very important ingredients to get things right for stars. And I didn't see a lot of, from what I've seen so far, not a lot of talks where people really do that.
All right. Thank you very much. Let's thank the speaker one last time.